Hey everybody, it's Mr. Gruber. Let's have fun with part B now. This one's kind of interesting because it's going to be one of those first times that we're going to see a not conservation of momentum problem. Now realize at the beginning of this problem we talked about one thing, which is, hey, there's an outside force because the track is not quite horizontal. There's an outside force, FG parallel, momentum is not conserved. What that means is the momentum will change, so the carts will accelerate as a system. So we have to look at the carts as a full system and invoke that equation we were dealing with earlier. And that equation was, I'll write it here before I scroll up. Let's do it in this purple, right? We know that F net has to equal M delta V over delta T for the system. Make that a little bit thinner. Let's undo it so we just see that F net equals M delta V over delta T of the system. And the M delta V of the system really is going to be the sum of the momenta of the system before collision. After final. Remember, it's delta, so it's final minus initial. So the initial sum of the momentum before the collision over time. Okay? So, once again, the net force has to be the sum of the momentum final before. I keep saying, I'm still thinking conservation momentum, which is we do before equals after. So, this is change in momentum, which is the sum of the final momenta of all the objects in the system minus the sum of the momenta initial. Got it. Now it's worded correctly. Okay, let's go label some things. Now remember, this here is a momentum versus time graph, so there's nothing to calculate as far as going with M times V. So you just leave it as P. So we'll use this one here as M1, right? So here's going to be our M1, and this one will be our M2. I know, it's like, well, that's 1 kilogram. Why did you have to make that M1? Because I just want to make the first one the one on top. So right here is our P1 final. Here is our P1 initial. Here is our P2 final. And here is our P2 initial. Okay? So we see that P2 final is about negative 0.6. And P1 final is about negative 1.3, positive 1.3, 1.3. It is kilogram meters per second. I hate leaving out units. Kilogram meters per second. And then P1 initial here, P1 initial has to equal, looks like about 0.3 kilogram meters per second. And then P2 initial equals about 0.2, about 0.2, negative 0.2 kilogram meters per second. All right, let's go plug that stuff in. Scroll up a little. Come on. There we go. Let's keep it in so I can see it, all right, because I want to be able to see the data. Come on, stop. Right there, good. Okay, so we got F net. Let's plug it in. Okay, so we got F net equals the sum final, which is going to be 1.3 minus 0.6. It's a sum, but the 0.6 is negative, so I'm just going to put minus 0.6. And then subtract that from the initial, which is 0.3. And then we're going to add the negative 0.2, which is the same as just saying minus 0.2, and put that over a time of 10 seconds. All right? And what does that give us? So 1.3 minus 0.6 is 0.7. So F net equals 0.7 minus 0.3 minus 0.2, which is 0.1. Put that over 10. 0.7 minus 0.1 equals 0.6 over 10, which is going to be 0.06 newtons. There's your F net. We have a slight net force acting on this system, which of course we said was FG parallel. Which brings us to the last problem on the last page, and which asks us, what if we change the individual masses of the carts. Nothing up there, right? So it says, suppose the experiment is repeated with different carts that the masses of a cart plus magnet are 2 and 4. Now remember something from the back, from page 25. Cart 1 was 5 kilograms. Cart 2 was 1 kilogram. So M total was equal to 5 and 1 is 6 kilograms, right? Oh, I'm going off page there. Let's put it over here. Let's move that. Come on. All right. So M total was 6 kilograms, right? Hello? Come on, seriously? I know that's going to write. Jeez. Great, awesome. Not a page. Come on, why do you got to do this? Such a picky iPad. Come on. Give me a second. Lock that in place. Okay. So what do we have now? Now we have cart 1 equals 2 kilograms. And cart 1. See, I'm doing it again. I'm making cart 1 2 and cart 1 4 kilograms. Hey, what's M total? Hey, 6 kilograms. Right? Hey, what was the net force on the system? FG parallel. Since the net force is due to the ramp not being level. I know it's not a ramp. I used the wrong word. It was a what do you call those? It was a frictionless thing. So, oh my gosh, we haven't used them all year because of the coronavirus closure. Air track, due to the air track. And what did they use? Let me just go look at the word they used. I don't know what they used. Let's be consistent with the language. Attach, make up a system. The figure frictionless track. All right, so we'll just call it a track. Okay. So, since the net force is due to the track. Track not being level, the net force is due to a component of the weight of the carts. Since the mass of the system hasn't changed, hasn't, let's try to write that correctly. Let's not use a contraction. Has not changed. So the mass system has not changed. The net force has not changed. And the net force has not changed. So the net force has not changed. That's it. The mass has not changed. The net force has not changed. And there's your first not conservation of momentum problem, and probably your last. I mean, the other ones are a lot more simple, where you just get a change in momentum from 2 different velocities, and that's it. Usually those are usually one object hitting an immovable object, like something hitting the floor. So the Earth, you really can't measure its momentum change. So the object that hits the floor and bounces up, its momentum changes. So momentum is not conserved. So we'll upload this, and you guys can watch it, and you guys have a great day. Good talking to you. Bye-bye.